Hi, this is Mrs. Wiederholt. I just want to welcome you to my lesson video on simplifying radicals, a review. Now let's get started. Now let's start this review by writing the square roots of each of the numbers below. I would hope that you would have them memorized up through 100, but if you don't, maybe this would be a good time to do so. So let's start out. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. Do you see a trend here? Our square roots are 1, 2, 3, 4, 5, 6. We're going to keep going. The square root of 49 is 7. The square root of 64 is 8. The square root of 81 is 9. The square root of 100 is 10. Now I understand after this, you may or may not know them. The square root of 121 is 11. The square root of 144 is 12. The square root of 169 is 13. And the square root of 196 is 14. Now, like I said, if you do not have these memorized, it would really help you to do so. Now, many times SAT questions will ask for an estimation of a radical. Now you can use your knowledge of perfect square numbers to determine what two positive integers the radical is between. So let's do that with this example and this example. The square root of 60 is between which two numbers? Now we're talking about which two square roots. Now if you look up, you can see that the square root of 60 lies between the square root of 49 and the square root of 64. Well, we know the square root of 49 is 7, and the square root of 64 is 8. So we could say that the square root of 60 is between 7 and 8. And for why? Well, I just explained that. The square root of 49 is 7, and the square root of 64 is 8. Now let's look at the square root of 19. Well, the square root of 19 would fall between 4 and 5. And how do I know this? Because I am looking for the perfect square that is just less than 19, which would be 16. And then I'm looking for the perfect square that would be just greater than 19, and that's 25. So that means that the square root of 19 falls somewhere between the square root of 16 and the square root of 25. Next, we're going to look at how we can be more specific, how we can go beyond just estimating our radicals. Simplifying radicals uses the foundation of prime factorization. Now, let's revisit middle school just a little bit and write our prime factors of the following numbers. I personally like to use the factor tree. Now, when creating a factor tree, I look at the number 20. We're going to start with that one. And I'm going to look at two factors of 20. Now you could say 10 times 2. You could say 4 times 5. Personally, I just go with what comes to my mind first. And 4 times 5 is usually what comes to my mind first. So now I have to look at the numbers 4 and 5. 5 is a prime number, so I'm done with that one. But 4 is not a prime factor or a prime number. I can divide 4 by 2. So 2 times 2 equals 4. Now 2 is a prime factor. So at this point, our prime factor tree is complete. So how does this help us with simplifying radicals? Well, let's look at the 2's. Anytime you have a pair of prime factors, that means they equal a perfect square. So since I have a pair of 2's, we know that 2 times 2 is 4. We know that 4 is a perfect square. And this knowledge will help us when we go to simplify the radical of 20, or the square root of 20, which we will do on the next page. Now let's find our prime factors of 60. Well, I'm going to start out, and 6 times 10 is what comes to my mind first. Now 6 is divisible by 2, and 10 is divisible by 2, so neither one of those are prime numbers. So we know that 3 times 2 is 6. Now 3 is a prime number, so we're done with that one. Oh, and 2 is also a prime number, so we're done with that one. Now let's go to 10. I know that 5 times 2 is 10. Okay, 5 is a prime number and 2 is a prime number. So we have completed our factor tree. But what I notice here is that I have, let me see if I can do this, a pair of 2's. I don't know if I did that very well, but since I have a pair of 2's, I know that I have a perfect square within the number 60. Now let's use this knowledge in actually simplifying some radicals. The first two that we're going to do on this page are the two that we did the factor trees for on the previous page. So let's start out with the square root of 20. Now there are several ways that you can show your work on this, and I'm going to do it like this. I know that the square root of 20 is the same as the square root of 4 times the square root of 5, and you can put them under one square root symbol. We've already said that the square root of 4 is 2. So once you take the square root of one of your numbers within the radical, it comes out. So now the square root of 4 is 2, and so the number 2 is no longer under the radical sign. But because we cannot take the square root of 5, it remains within the radical sign. And so that would be your answer. That's the simplified version of the square root of 20. Now let's simplify the square root of 60. Well, if you remember on the previous page, when we did our factor tree, we ended up with a pair of 2's, which would be 4. So the square root of 4 times, and we had 3 and 5, so that would be 15, 3 times 5. So the square root of 60 is the same thing as the square root of 4 times the square root of 15. Well, the square root of 4 we can do because 4 is a perfect square. Square root of 4 is 2. But 15 is not a perfect square, so it will remain under the radical sign. And so there you go. The square root of 60 is simplified to 2 times the square root of 15. Now let's simplify the square root of 40. The square root of 40, I can factor it to 4 times 10. And y'all, this is where the prime factor tree would help you. If you do not already know that one of the factors could be 4, 4 is a perfect square, then use your factor tree in the method I showed you on the page before. So the square root of 4 is 2, and because 10 is not a perfect square, it will remain inside the radical sign. So the square root of 40 is simplified to 2 times the square root of 10. Next, let's look at the square root of 128. Well, I know that 128 could be written as 2 times 64. So the square root of 2 times the square root of 64 is the same thing as the square root of 128. Well, 2, I cannot take the square root of that, so it will remain under the radical sign. But 64 is a perfect square, and the square root of 64 is 8. So I can rewrite this as 8 times the square root of 2. Now let's look at the square root of negative 45. Well, I can write that as the square root of negative 1 times 9 times 5. And 5 is not a perfect square, so it's going to have to stay under the radical sign. And what is the square root of negative 1? Remember, that's our complex number. We would write that as an I. But I can take the square root of 9 because 9 is a perfect square. So these are the two that are going to come out of the radical sign. The square root of 9 is 3, and the square root of negative 1, remember we write as I. And then what will remain in the radical sign is the 5 because it's not a perfect square. So I would write that as 3i times the square root of 5. Now let's move on and see how we can simplify radicals when they have variables with exponents. In order for us to simplify radicals with variables with exponents, first we need to take a look back at how to change a radical to something in radical form to rational form. So first I want us just to take a look at x to the third power. Now remember, if you had x to the third power, or the square root of x to the third power, and you wrote that in rational form, that would be x, remember the radicand is your base, and then the exponent of the radicand becomes the numerator, and then the index, in this case invisible 2, becomes the denominator. So basically, the square root of x to the third power is really just x to the 3 divided by 2 power. So what this means is when you're trying to take the square root of a variable that has an exponent, if the exponent is even, then your variable is a perfect square. If the exponent is odd, that means it's not a perfect square, and I'll show you what to do with that on this first problem. So let's expand the square root of 18 times x to the third power. I know that 18, the factors of 18 are 9 times 2. Now, x to the third power, 3 is an odd number, so I am going to expand this to be x squared times x to the first. Now, you don't have to show the 1, I just am for teaching purposes. Now, the square root of 9 is 3. 2 is not a perfect square, so it will stay within the radical sign. Now, since I have x squared, remember that's an even exponent, so it is a perfect square. And the square root of x squared is x. And then I have left the x to the first power, and that is not a perfect square, so it will stay within the radical sign. So my answer would be 3x times the square root of 2x. Now let's move on to the next one. The square root of 32 times a to the 6th times b to the 8th. Okay, I'm going to expand this one. Factors of 32. 16 times 2. Now, do you notice that the 6 and the 8, my two exponents here, they are even numbers. So that means I don't have to expand them. A to the 6th is a perfect square, and b to the 8th is a perfect square. Okay, so here we go. 16 is a perfect square, and the square root of 16 is 4, so that comes out of the radical sign. A to the 6th is a perfect square. Now remember, all you're doing is you're taking that exponent and dividing it by 2. That's how you take the square root of it. So a to the 6th divided by 2 power would be a to the third power, so that comes out. B to the 8th is a perfect square, and that would be b to the 4th. So the only thing remaining in the radical sign is the 2, which was not a perfect square. So the simplified version is 4 times a to the third times b to the 4th times the square root of 2. Now let's look at 7 times the square root of 9 times x to the 11th power. Now with 7 being on the outside, we leave it on the outside, and you'll see what happens to it in just a minute. Now 9 is a perfect square, so I don't need to expand that. But x to the 11th is not, so I need to expand it to x to the 10th power times x to the first power. Okay? Now, the square root of 9 is 3. So on the outside, I have 7 times 3. And then the square root of x to the 10th would be x to the 5th power. And the only thing remaining in the radical sign is the x. So now I just need to multiply 7 times 3, which is 21. And so my answer is 21 x to the 5th power times the square root of x. Now let's look at 5 times the square root of 20x squared. So again, I have 5 on the outside, and I'm going to expand 20 to 4 times 5, and because x squared has an even exponent, I do not need to expand that. 4 is a perfect square, so I can take the square root of 4, which is 2, and it goes to the outside. X squared is a perfect square. That would be x to the 2 divided by 2 power, x to the first. And so the only thing I have remaining is the 5 that was already there. Multiply the 5 times 2 on the outside, and you will have the answer of 10x times the square root of 5. Now let's look at the last one. I have negative 9 times the square root of 8x. Again, negative 9 is on the outside, and I need to expand 8 into 4 times 2, and then x, that's only x to the first power. So it is not a perfect square and will remain under the radical sign. 4 is a perfect square, so on the outside I now have negative 9 times 2, because the square root of 4 is 2. And then on the inside of the radical sign, I have 2x, because those are not perfect squares. So the only thing left to do here is negative 9 times 2, which is negative 18 times the square root of 2x. So there's the simplified version of that. Now before I close today, if you are one of my students watching this video, I need you to now go to Edmodo and answer a few questions on a quiz that I have for you. I hope this video has helped you in understanding how to simplify radicals, and I look forward to working with you again. Bye-bye.